the third and final day of the supergravity and holography workshop. Before starting, I would like to again reiterate and really thank the MITP for giving us the opportunity of organizing this workshop and to give us the possibility of discussing with friends about physics. Today's plan is made of two talks with a small break of 10 minutes between them. After the two talks, we will have a 20 minutes break, and after that we will have a one hour long discussion session. So the speakers today are Rodrigo Olea and Oliver Amiskovic. Since we are already ready with the screen by Rodrigo, it's a pleasure to introduce Rodrigo from the Andrés Bello University in Chile. He will talk about conformal renormalization of anti-de Sitter gravity. So the stage is yours, Rodrigo. Go on.
Thank you very much for the presentation, the introduction, and the invitation to give this talk. I'm really grateful for the possibility to present my recent work and some things that I have been developing throughout the years. It's a long story. I had to make it short, but I will try to go straight to the point. And what is the title of the title of the seminar is still something fast developing. I would loosely call conformal renormalization, even though it's some work in progress with the collaborators in different places. So what is my motivation for the talk? My motivation for the talk will be, as you know well, and it's one of the parts of the topics of the conference, of the workshop, is holographic properties of asymptotical AdS gravity. And I would just briefly touch the concept of supergravity. I would just mention some connections. I hope that this can be extended to, in some aspects, to supergravity as well. And I will be glad to discuss with any of you who is interested to try to address any of the open problems that this is considering. Because here we are solving some issues, but we are also opening a lot of new avenues and future directions of work. So I will make a lengthy introduction of what had been called counter terms with a K. That is not a typo. I will try to convince you that there is no typo there. And as an alternative renormalization scheme in AdS gravity, I will develop, to a certain extent, I will develop the connection between standard counter terms in AdS gravity and this new alternative proposal. And I will comment, I will first suggest, and after that I will more formally comment on the appearance of conformal structures in the bulk and a possible connection with, in general, with the conformal gravity. So let's go straight to the point. In the holographic picture, this is the usual AdS CFT dictionary that in order to compute a partition function for the corresponding boundary field theory, you had to approximate that by the exponential of the gravity action. What is intended here is that you are taking a bulk field that is approaching to the boundary value that is called phi naught in this case. And in order to do such a thing, you usually, because of the asymptotic behavior of AdS gravity, you have to consider a mechanism to render the quantities finite or renormalized. So in the simplest case, when you have pure gravity, you have to describe in terms of a metric tensor, which is in asymptotically AdS behavior, is characterized by a pole of order 2 in the conformal boundary. So we will extensively make use of the fact that any asymptotically AdS spacetime can be written in this Fefferman-Graham form that is very similar to the Poincare semiplane, and where the holographic coordinate, the holographic radial coordinate, normal to the boundary, will be the set coordinate. So as I was suggesting, there is clearly divergence of order 2 if you consider a regular metric at the boundary, like this, like the one I'm showing now. So I will consider that the metric can always be expanded as a power series of the set coordinate, and is the conformal boundary is characterized by the conformal data, that is G0. What is the idea behind this? Is the idea of holographic reconstruction of the spacetime. You fix the boundary data, the conformal boundary, and order by order into the equation of motion, into the Einstein equations. You try to solve all these coefficients in the expansion as covariant functionals given by this metric at the boundary, this G0 metric at the boundary. So what do you expect? You expect, for instance, G2 to be expressed in terms of curvature associated to a certain number of covariant derivatives in terms of the G0 metric. They are covariant functionals. So this makes you keep control on the type of divergences that appear at the level of the action and the variation of the action. So you have a systematic way of canceling these divergent terms that appear there. This in turn implies the fact that you would need, at the level of the action and its variation, you would need the addition of boundary terms, which act as counter terms in this case. Counter terms in the sense of infrared divergences that appear at the level of the classical gravitational action. So what are these covariant counter terms? They have to be expressed in terms of the boundary metric, the boundary curvature, and other covariant functionals of the intrinsic quantities. Why is this prescribed in this way? Because on top of the bulk action, the standard Einstein-Hilbert action with negative cosmological constant, you have to consider a Gibbons-Hawking term, which sets a properly defined variational principle for keeping the metric fixed at the boundary. So this is, when you do it in this way, you are keeping, when you add the Gibbons-Hawking term, you are setting this Dirichlet action principle. And that's the reason why on top of the Gibbons-Hawking term, you cannot add purely intrinsic quantities. Otherwise, you spoil, naively, you would say that you spoil the variational principle for the boundary metric. So what this is, what at the end of the day this produces? You can define something that's called a quasi-local stress tensor, or Brown-York quasi-local stress tensor at the boundary, defined in terms of as functional variation respect to the boundary metric. This will have essentially two contributions. The first is defined just by the addition of the Gibbons-Hawking term, is what is called canonical momentum. Canonical momentum defined in terms of derivatives of the evolution associated to the radial direction instead of the standard time-life foliation in ADM formalism. So the first contribution that is produced by the Gibbons-Hawking term is the canonical momentum, and the rest of the contributions coming in the Brown-York stress tensor are necessarily coming from the addition of counter terms, standard counter terms on top of the Gibbons-Hawking. So what is this useful for? It's useful to define holographic quantities, because if you take this Brown-York stress tensor and you simply rescale it by a certain power of the holographic radial coordinate, you multiply this Brown-York tensor and you multiply it by a certain power of the radial coordinate, and you take the limit, you can obtain holographic quantities. This is the holographic content of the theory. It's the one that you obtain as correlators in terms taking functional variation with respect to G0 metric at the conformal boundary. And this is holographic. And so this holographic information of the theory is encoded, for instance, in the corresponding trace of the holographic stress tensor, that is the Weil anomaly. And this is a criterion, for instance, that helps you to identify what is the corresponding boundary CFT you are inducing, I mean, in the gauge gravity dictionary. So just to give you a flavor of what these usual standard counter terms look like, I would say I will list here the first terms of the counter term series. In a given dimension, you don't need, in low enough dimensions, you don't need all these counter terms because there is a power counting argument that if you apply this power counting argument, it's easy to identify how many counter terms you need in a given dimension. In low enough dimensions, you will need, for instance, 3 dimensions, you will need only sort of cosmological constant at the boundary. In 4 dimensions, you will need the first 2, and also in 5 dimensions as well. And as you go up in the dimension, you will need extra counter terms to be added on top of this. So the basic prescription of this is what I was saying. Whenever you compute the renormalized Brown-York stress tensor, you will have a contribution coming from the canonical momentum, which is linear in the extrinsic curvature, and the rest of the contributions are purely intrinsic. This is a very important thing because I will use this as a motivation to introduce nonlinear contribution at the boundary of the extrinsic curvature. So this is something I would like to emphasize at this point because I will use it later as a motivation. And my usual motivation is the fact that there is no general form to write it down the full counter term series in an arbitrary dimension. Or if you change the gravity theory and you want to work out the holographic description of this higher derivative, higher curvature gravity theory, it would be much more difficult to perform such procedure as holographic renormalization. I must admit that, I mean, it's a well-known systematic procedure, but it doesn't mean that it can give you the answer for all the dimensions, for instance. So that's the reason why you have to start thinking in a different way if you want to try to propose something that is alternative to this holographic renormalization procedure. And I will make a few observations at the verge of triviality that actually, even though they are almost trivial, they produce the fact that you can consider a different way of renormalizing the action. The first observation is the fact that, as it was pointed out in this paper, a few years after the first paper of holographic renormalization, it was pointed out in similar papers of this period that a Dirichlet boundary condition for asymptotical AdS spaces does not really make sense. And it doesn't really make sense exactly because of the asymptotic behavior of the metric. The asymptotic behavior of the metric, if you write it down in Pfefferman-Graham form, it reflects precisely the divergent behavior of order 2 and the conformal boundary. So actually, the only thing that makes sense is the fact that you can fix G0. It's like the holographic picture. And whenever you consider the holographic picture and you want to truly fix G0 at the conformal boundary instead of the full metric, you end up relating renormalization with a variation principle that is expressed in terms of the holographic source. That is, of course, suitable to deal with in the holographic in a holographic picture. Because as long as you have an action, a renormalized action, that is finite and is expressed in terms of variations of the holographic source, you can call it holography. And so the first observation I would make is the following fact. If you take the asymptotic form of the extrinsic curvature instead, the asymptotic behavior of the extrinsic curvature has exactly the same behavior of the boundary metric. So if you consider the addition of boundary terms that contains the extrinsic curvature, you may end up with variations of the action that are anyway expressible in terms of variation of the holographic source. So it's absolutely possible to add at the leading order. You would notice that there is practically no difference between adding terms, intrinsic terms and extrinsic terms. That opens the possibility of adding terms that depends on the extrinsic curvature, or nonlinear terms that depends on the extrinsic curvature as well. Because everything can be, at the end of the day, the net effect may be the same. So this is exactly what I'm saying, that they may be counter terms of a different sort. You may add boundary terms that depends on intrinsic quantities but extrinsic quantities as well, in a nonlinear way, not like Gibbons-Hopkin term. And as long as your final variation of the action is holographic. What does it mean? Holographic means that it's finite and that is expressed in terms of variation of the holographic source. Why I call it tau instead of t? Because until this moment, it's not guaranteed at all that it will produce the same holographic correlators. This I don't have theorem proving that such a thing is always possible. And I'm just suggesting the fact that you may add something at the boundary that depends on the extrinsic curvature in such a way that the holographic picture is not broken. So what I will consider is exactly this: I will consider the addition of bounded terms that depends on the extrinsic curvature such that the variation of the action is finite and is holographic. The other piece of evidence to try to motivate the introduction of nonlinear contribution at the boundary that depends on the extrinsic curvature comes from the following considerations, rather technical. I will simply say that one of the most basic definitions of energy in asymptotically AdS spacetime is this one that is called conformal mass. Conformal mass is nothing but certain contraction of what is called the electric part of the Weyl tensor. The Weyl tensors have 4 indices, and if you contract 2 indices with a normal to the boundary, that is this normal n that is essentially orthogonal to the boundary, you will be left with a quantity that has only tangential components along the boundary, this ij. And what are the essential properties of this electric part of the Weyl tensor? One of the basic properties inherited from the fact that the space-time Weyl tensor is traceless. So the electric part of the Weyl tensor is also traceless. And if you work out the expression of the quasi-local stress tensor, you will realize that some difference respect to the electric part of the Weyl tensor may appear at a holographic order. So in turn, the quasi-local stress tensor has a trace because it had to give rise to the anomaly. But you can prove, until certain dimension, you can do it. For instance, in 5 dimensions, people have proved that actually the quasi-local stress tensor is almost the electric part of the Weyl tensor, and they may differ by a quantity that produce the Weyl anomaly. And the Weyl anomaly appears at a holographic order, a very high order. So in simple terms, I use this as a motivation to say that is quasi-local stress tensor and electric part of the Weyl tensor are almost the same, but to the, up to the holographic order, they're almost the same. So if you work out an expression for the electric part of the Weyl tensor in Gauss normal coordinates, and you use this Gauss-Corazzi decomposition, it's quite surprising that you would be able to express the standard, the quasi-local stress tensor in as a quadratic expression in the extrinsic curvature. And this is an open contradiction with what I just said before. I show you that in the standard holographic renormalization picture, the stress tensor is linear in the extrinsic curvature because it's just the extrinsic curvature just appear in the definition of canonical momentum. So you can consider this reasoning in two ways. You can start thinking that maybe these counter terms that appear in the holographic renormalization scheme, they may be a linearization or a truncation of nonlinear boundary terms in the extrinsic curvature. Or the converse argument, it would be that some of the expansion of the counter terms may be summed up into extrinsic curvature terms. So maybe all these series that you saw very complicated, maybe could be at the end of the day, the sum up as extrinsic curvature contributions. And I will show you in a few minutes that this is exactly the case. Are the questions as far? No. So, okay. So I will call now, I will go straight to the point. I will call that there is such a thing as extrinsic counter terms in AdS gravity. And of course, you would have multiplicity of possible choices of what to construct at the boundary. It's a practically infinite combination of extrinsic curvature, intrinsic curvature that you could propose. But because we were somehow well informed, we proposed in a certain moment, there was a proposal that it was very geometric. It had a very geometric origin. That is nothing but the Chern form, the corresponding Chern form. Let's say at the boundary of even dimensions, there is a sort of Chern-Simons form. It's a Chern-Simons for the Lorentz group, and it can be expressed in terms of the extrinsic curvature. Some of the people in the audience will be wondering why this parametric integral, and I will briefly comment on this is a typical trick in Chern-Simons derivation. This is a consequence, it's an explicit realization of the homotopy operator that makes you write down the Chern-Simons form as a parametric integral. And this is a polynomial. It's a highly nonlinear polynomial of the extrinsic curvature and the products with the intrinsic curvature, but it's a well-known object in the literature. So that's the reason why we proposed it in a certain moment, and we proved that to a certain extent we were able, based on explicit solutions, we were able to render the action finite. Okay, this is more or less understood at the boundary of even dimensions, more or less a posteriori is quite expected to appear Chern-Simons form. The problem was, to be honest, how to deal with the other case, the case where the space-time is odd-dimensional. And there is no such a thing at the boundary like Chern form. But we were guided by the same principle, like trying to construct a polynomial that it was a polynomial of the extrinsic and intrinsic curvatures, and we were able to propose something that didn't exist in the literature, but it has also the compact form This time is expressed in terms of double parametric integral that I will try to suggest where it comes from. This is typical tricks in the context of anomalies. So what is the connection with what people know in the literature? Of course, it's pretty obvious that in the even dimensional case, this is connected to topological terms. Whenever you have an even dimensional manifold, you can define a topological term of a corresponding group, like the trace on the generators of the group of the field strength to a certain power. And this is locally equivalent to a Chern-Simons form where the connections is a Lie algebra valued connection. So this is for any group, and in particular for the Lorentz group, what you produce is of course the Euler term in the bulk, and what you produce at the boundary is this Chern form expressed in terms of the extrinsic curvature. So in order to realize what is the explicit form of the Chern-Simons densities, you have to use this parametric integral. This is a typical trick in order to write down this expression in a very compact form. And that's the reason why in the previous slides, I show this in this very compact notation. So if you take care of global issues, you would simply say that these Chern forms are equivalent to topological terms of the Euler class up to the Euler characteristic of the manifold. This is topological number that at the level of dynamics, it doesn't play any role, but it becomes relevant for other considerations. We have discovered in a completely different scenario in the context of holographic entanglement entropy, this Euler characteristic plays an essential role in the computation of holographic entanglement entropy. But it's not the case here. We are dealing with just dynamics. So I would simply call it, I would simply say that these Chern forms are locally equivalent to topological terms. In the odd dimensional case, it's far more complicated. We don't have a clear reason why this sort of term should appear at the boundary of odd dimensional AdS gravity. The only thing that I can mention that similar structures appears in the literature. There is in odd dimensions, and this had nothing to do with Einstein-Hilbert gravity. In odd dimensions, there is a gauge invariant extension of Chern-Simons form, what is called transgression forms. Transgression forms are written in terms of the difference between two gauge connections. Let's say A and A bar. This is a typical trick that people play in order to extend the Chern-Simons form that is true, not truly gauge invariant under large gauge transformations. So you can go and find papers and lecture notes in the 80s, and it would say that this transgression form can be always written down as the difference between two Chern-Simons, one associated to A, one associated to A bar, plus a contact term, something where these two connections talk to each other, and this is a mixing of the terms coming from A and A bar. And this also had a very suggestive form because this time is written down in terms of this double parametric integral. I'm not claiming whatsoever that this had a direct relation to what I just showed, but it's very suggestive form, and that's the reason why this double parametric integral appears everywhere as well. But it's not quite, it cannot be derived directly from this consideration, unfortunately. So it doesn't have a purely group theoretical interpretation, I would say. So at a very practical level, what does it mean? For instance, if I want to compute standard black hole thermodynamics. I want to evaluate Schwarzschild. I want to evaluate the Euclidean action in Schwarzschild AdS black hole. What are the consequences of this proposal? I would say if you evaluate the bulk action, the Euclidean bulk action, you will get a fraction of the mass. From the bulk action, you will get the right entropy at the horizon, and you also get a divergent term because you can use the equation of motion and prove that the Euclidean action is proportional to the volume. And the volume, you have to integrate the volume between the horizon and infinity. The contribution of the horizon, it produces the entropy, and the contribution at infinity, it will produce a divergent term. So, curiously enough, the evaluation of Euclidean counter terms with a k, it will produce the other fraction that you are missing from the internal energy. It will produce something that in the context of AdS CFT is called vacuum energy, that from the point of view of the boundary CFT is the Casimir energy of the corresponding boundary field theory. And you will produce a divergent term with the opposite sign. So it's, in a very simple example, it's pretty clear that these counter terms with a k are helpful to get rid of the divergences at the level of the Euclidean action. So you cancel divergences, you contribute with the fraction, the missing fraction at the level of the internal energy, and you reproduce the right thermodynamics, where the internal energy is shifted by a quantity that had to do with what is called vacuum energy or Casimir energy in the context of CFT. So we arrive to the point where we want to compare with standard procedure. What it have to do topological terms or Ken-Simons forms with the standard holographic renormalization, because this is just a very well-informed guess, but we have not proved anything at all. And I would say in the simplest case, in the four-dimensional case, you should proceed in the following way. It's slightly technical, but someone had to do the job. And you propose that you have to add the Chern form on top of the Einstein-Hilbert action. In the Chern form, there is nothing like the Gibbons-Hawking term. The Gibbons-Hawking term is proportional to the trace of the extrinsic curvature. It's linear in the extrinsic curvature. Here, there is nothing linear in the extrinsic curvature. So what you have to add, you have to add a zero. You add and subtract the Gibbons-Hawking term. You add the Gibbons-Hawking term and you subtract the Gibbons-Hawking term, because here, these deltas multiplied by these antisymmetric deltas will produce the trace of K. And this is minus the Gibbons-Hawking term. So you are adding zero to the system. And when you do such a thing, the rest is using the standard holographic picture to expand and to convert extrinsic contribution into intrinsic ones. How? Pfefferman-Graham is an expansion number of derivatives at the boundary. So you can express it in terms of expansion, in terms of curvatures associated with the boundary geometry. So the first contribution had no curvatures, so no derivatives. The first contains two derivatives, so it's proportional to the Ricci and Ricci scalar. This is particular combination of the Ricci and the Ricci scalar is the Schouten tensor. So the Schouten tensor will show up there, and the rest are higher order contributions in the intrinsic curvature. So in this way, you can convert extrinsic contribution into intrinsic ones and try to perform a comparison. And in the four-dimensional cases, you just collect terms. You collect terms with no derivatives, with one curvature, with two curvatures, and so on, and you manage to reproduce the standard Balosura-Mannian-Krauss counter terms from the addition of a Chern form to the boundary. So it's actually standard counter terms this far are coming as a truncation of geometrical object like chain form. So it's very interesting to relate this to, as we will see later, to topological terms. So you would say that standard counter terms in the holographic renormalization picture come from the addition of these extrinsic terms. Let's see if we have lag in higher dimensions. This is far more complicated. You proceed in a similar fashion. You have no Gibbons-Hawking term. You force the system to have a Gibbons-Hawking term. Add and subtract the Gibbons-Hawking term, and then you expand. And the computation is slightly difficult, but after cranking the machine, you have this form that is rather unusual, because in the expression that I showed before, there were no contributions of the type Riemann square terms. So this is rather unusual form of the standard counter terms, but then you remember that if you express everything in terms of the Weil tensor square, you can trade off Riemann square contribution by Ricci square and scalar curvature square. And at the end of the day, what you show is until here, until this part, there is perfect matching with a standard holographic renormalization procedure. So if you ask me, and this is the key point of the seminar, is the R counter terms with the K the same as holographic renormalization? You could give two answers. The pessimistic is no, because to be honest, it's no. But the optimistic would be almost. Why? Because there is a mismatch of this type of terms. And of course, as you go up in the dimension, the mismatch will be more additional terms eventually. What are these terms? These terms are identically zero for asymptotically conformally flat geometries. So for Schwarzschild black hole, for Kerr black hole, everything matches. You would be able to reproduce the black hole thermodynamics associated to this. But eventually, you may consider more non-trivial boundary geometries with non-vanishing Weil tensor. So for instance, gravitational instantons like tau nat in higher dimensions, this eventually will cause problems. Because of a power counting argument, this sort of contributions may be even divergent. So these are potentially dangerous terms if you want to evaluate everything in a non-trivial geometry. So, of course, you may think that you have the alternative of matching up the theory and putting everything that is in this side to the other side and repairing the theory. But somehow this is very ugly as something to be done. And so at this moment, I arrive to the motivation of my seminar today, because I'm trying to patch up this problem, but in a very fundamental way, not just simply throwing everything what is garbage to the other side or hiding that under the carpet. So I will try to correct this problem that appears in a more systematic and fundamental way, and I will try to present new evidence of how this should be connected to some conformal structures that appear in the above. So in order to do so, I had to be very sort of provocative. I had to try to motivate the existence of conformal structures. And let's see how it goes. So I told that I could always trade off chain form by topological terms. If I do such a thing, I use the Euler theorem, I trade off this chain form by a topological term, by Gauss-Bonnet. And the Gauss-Bonnet will come with a precise coupling, this L squared over 64 pi g. This will appear. So I go back to the original way we found it from the point of view of the conserved quantities of the with this, the first observation that was made by us long time ago, Aros, Zanelli, Troncoso, myself, and we used this procedure at the level of the conserved quantities of the theory. We didn't do it at the level of the Euclidean action. So let's consider, and this, because this is a supergravity and holography, I want to emphasize the fact that in a completely different picture, this Gauss-Bonnet coupling is also singled out by supersymmetric arguments. If you keep track of all the boundary terms that come from supersymmetric transformations, it was pointed out by Laura and Ricardo that the fact that the Gauss-Bonnet coupling also had to be fixed in the same way. So you end up with this bulk action that is renormalized. Now we know that it's exactly the same as holographic renormalization. So this renormalized action is nothing but McDowell-Mansouri action, an action that becomes quadratic in this quantity. What is this quantity? This is a quantity that is the Riemann tensor plus skew-symmetric product of the metric that is nothing but the curvature associated to the AdS group. The AdS group had the connection of the AdS group has the spin connection along the rotation generators and the field line along the AdS translations. So the curvature associated to that group is this object along rotation generators and the torsion along the translations. So if you think of Riemannian geometry, this is the only surviving component of the curvature associated to the AdS group that I will emphasize during the rest of the talk. So renormalized action is McDowell-Mansouri at the end of the day. So why this is very appealing as an idea? Because of the following observation. Let's take the Weil tensor, the generic definition of Weil tensor. The Weil tensor is the Riemann tensor and the skew-symmetric product between the Schouten tensor and the metric. And let's take the Weil tensor for an Einstein space. The Weil tensor for an Einstein space is characterized by a curvature, by a Ricci tensor that is proportional to the metric. If you plug it in here, in the definition of the Schouten tensor, and later in the Weil tensor, that's the reason why I put a subscript E for Einstein. So the Weil tensor for an Einstein space is nothing but the AdS curvature. So these two notions of curvature coincide in Einstein gravity. This is what I wanted to emphasize at this point. So at the end of the day, on shell, the value of the action is very suggestive. We are still in Einstein gravity, where I'm not claiming anything about conformal gravity yet, but it's very appealing to notice that the value of the action is nothing but Weil squared evaluated for Einstein space-time. And it's also very appealing because, for instance, if you want to use this result to evaluate black hole thermodynamics, the thermodynamics of pure AdS or global AdS is identically zero because the renormalized action is identically zero. The charges that you may derive from this action, they're identically zero. And remember that the black hole entropy is the nether charge evaluated at the horizon, so it's identically zero. So the minimal consistency check that you have to perform in an action is the fact that everything is consistent for the, you would say, the vacuum state, the global AdS spacetime. So in this way, you make your theory independent of the background, or you set the background. You define the background in this way. You define the background as the space-time that makes everything zero, that turns everything trivial. So in this way, you make your your gravity action independent of the background metric, for instance. You don't have to subtract anything to the gravitational action. So the idea, because of the previous result, we came with this idea of embedding, in a way, embedding Einstein gravity in conformal gravity. Why? Because any solution, it happens in 4 dimensions. It's happened that any Einstein solution is also a solution of conformal gravity. It's far more difficult to prove such a thing in higher dimensions, but at least in 4 dimensions, there is always an Einstein sector in conformal gravity. What is conformal gravity? In 4 dimensions, I will show the equation of motion. Why we came with this idea? Because in general conformal gravity, for this Pfefferman-Graham expansion, even including higher derivative modes, the action will be finite. Classical gravity action will be finite. So in a way, the idea that we have behind of this is that renormalization in the Einstein sector will be inherited from the conformal gravity properties. So recapitulating is we embed Einstein gravity in conformal gravity, and we think of a mechanism to go back to Einstein gravity. And in this way, we will be able to renormalize the Einstein gravity action. So how we will do this? How we will go and embed in conformal gravity? We have to ask for a conformal gravity that has an Einstein sector. And how we will go back from a generic conformal gravity solution to Einstein gravity? There had to be the requirement of such a thing to have a well-defined mechanism to switch off certain modes in such a way that it can go between a genetic solution of conformal gravity back to the Einstein branch of the theory. So that's the reason why I think of this system of switching off certain modes to go back to the Einstein sector of the theory. And this can be realized holographically. And this is what I want to show in the next slide. So what is this holographic mechanism I'm talking about in the 4-dimensional case that will be the key also to try to solve it in higher dimensions? So there was a proposal by Maldacena 10 years ago of converting conformal gravity into Einstein gravity by a precise boundary condition. In a holographic description of higher derivative gravity theory, there is the generic Pfefferman-Graham expansion. I was telling before that an Einstein metric is characterized by even powers of the Z coordinate. If you consider the addition of a different mode, this will be a result of higher derivative equation of motion. So in principle, in conformal gravity, there is a new source in the system, and there is a new response to this source. There is a new holographic stress tensor associated to higher derivative modes. So in principle, Maldacena, what he say, that demanding Neumann boundary conditions for the metric, he was able to cancel this G1 contribution. And in this way, you go back to the Einstein branch of the theory. And you can compute everything, and everything will behave like it was the Einstein sector of the corresponding theory. So what are the equations of motion for conformal gravity? Conformal gravity is characterized by equation of motion, field equations which are 4 derivative. Is expressed in terms of what is called Bach tensor. The Bach tensor considers covariant derivatives of the Cotton tensor. The Cotton tensor is a two-form. Is the antisymmetric covariant derivative of the Schouten tensor, plus the Schouten tensor contracted with the Weil tensor. this is equal to 0. This is the equation of motion. It's a hard derivative gravity theory. We realize, we try to realize this as a holographic picture. So because Einstein spaces has a constant Schouten tensor, 0 Cotton tensor, and 0 Bach tensor. So we try to map these conditions into what is called the traceless Ricci tensor. The traceless Ricci tensor for an Einstein space is identically 0. You can prove such a thing. And what are the implications of the traceless Ricci tensor? Are exact whenever you demand an Einstein tensor that is 0 traceless Ricci tensor, you have the Maldacena prescription, this Neumann boundary condition, and you have the rest of the consequences that we also saw at the holographic level. And because the equation of motion of conformal gravity are higher derivative, there is a lot of free data in the system. You cannot fix the intermediate powers. And we consider that anyway, because you are dealing with asymptotically AdS spacetimes, this free data can be chosen as in the Einstein branch of the theory. And this can be done by a purely kinematic description that is called Penrose-Brown-Henault transformations, are the transformation that preserve the asymptotically AdS form of the metric. And this is contained in this paper that is as I stress, is a purely kinematic description. So you have the freedom to choose the intermediate terms in this way, and you go back to the Einstein branch of the theory. So doing this, you have a well-defined mechanism to pass from, at the level of the action, you pass from Weyl square term to Weyl squared, but from the Einstein space. And this is exactly McDowell-Mansouri action, and this is exactly renormalized action for Einstein AdS gravity. So this was our inspiration to try to produce something in higher dimensions, at least in 6, that it was complicated enough. Are the questions this far? If not, just proceed. So let's try to imagine something similar in 6 dimensions. In 6 dimensions, what I say as that we were trying with topological terms. We were adding this term form, which is locally equivalent to add a topological term that is Euler 6. So we have Einstein-Hilbert cosmological constant and a topological term. This Einstein-Hilbert, that is, we know well that it doesn't match holographic renormalization results. So let's try to imagine something similar. I'm just writing down the previous line in a fancier way. This is Einstein-Hilbert term, written like in 4 differential forms. This is cosmological constant, and this is the Euler 6 term. Just simply write it with this totally antisymmetric Kronecker delta. And this is, the next step is very somehow appealing, because we managed to reduce the previous action to a polynomial of the Weyl tensor, the Weyl tensor evaluated for Einstein spaces, which are essentially 2 contributions, Weyl squared and Weyl cubed. It's totally antisymmetric product between the 3 Weyls in this case. And why this is appealing? Because if you go and express, and you take, and you consider conformal gravity in 6 dimensions, and if you go to a precise basis for this conformal invariance, there are 3 conformal invariants in 6 dimensions, which are essentially certain contraction of Weyl cube, other type of contraction of Weyl cube, and Weyl box Weyl, and Weyl squared Schouten tensor. This is not so obvious, plus a derivative. This is not illuminating comment, but what I will show is a precise combination of these three conformal invariants. There is a precise combination between these two conformal invariants that produce this bile contracted with a totally antisymmetric Kronecker delta, with a precise coefficient. With a precise coefficient, everything can be written as the previous slide. And there is a precise combination of these three conformal invariants, which can be written in this way. Can be written like bile cube, bile Schouten, because for Einstein spaces, Schouten is a constant. So it reduces to bile square. Cotton tensor is identically 0 for Einstein spaces plus total derivatives. So with this idea in mind, we realize that there is a precise combination of these three conformal invariants that is what it already existed in the literature. It's called Lu, Pang, and Pope conformal gravity that has an Einstein sector. And this is the exact combination that appears in the type B anomaly from the point of view, whenever you compute the anomalies of 7-dimensional Einstein gravity, what appears at the boundary is this precise Lu, Pang, and Pope combination of conformal invariants. I don't have an explanation for that. It's an open question. But it was very appealing, expressing everything in terms of the bile, the cotton, and the Schouten in such a way that we managed to prove in this paper with Yorgos and Ignacio, we managed to prove that any Einstein space is a solution of this particular conformal gravity. And what it goes together with this picture that I'm trying to embed Einstein gravity in conformal gravity. First of all, I have to find the conformal gravity where Einstein can be embedded. So a basic requirement of such a thing is proving that Einstein solutions are a solution of this particular conformal gravity action. So and at the same time, you may anticipate that all the bile tensors reduced to this bile of Einstein. So this will be bile cube, bile squared. This will disappear, and there will be eventually additional contributions. So this is exactly what we did. We separated the contribution in Einstein and non-Einstein. The non-Einstein part disappears when you take the limit of recovering Einstein. And this is exactly choosing appropriately the coupling. This is exactly Einstein-Hilbert, Euler-6, but the surprise is that there is an additional term. And the additional term, you can work it out in holographic expansion and so on. And to make the story short, because this is rather technical, the extra terms that appear cures the problems of the topological term that I showed before, in such a way that when you take conformal gravity of Lu, Pang, and Pope, you evaluate in the Einstein, you take the Einstein condition in this action. This is holographic renormalization action. This is the action prescribed by holographic renormalization. So it's very appealing as a concept that I can formulate in a single line. I can tell you what to do instead of adding counterterms, endless counterterms, and so on. I can tell you that in order to get a renormalized action, the only thing that you have to do is to embed in conformal gravity. I don't have a generic proof of this claim. We are working on. We are working on the higher dimensional case to try to find evidence to make such a claim in general. So, just as a summary of my results, I have shown something that is rather mysterious to me yet, but is what we found, that we were able to embed Einstein gravity in conformal gravity, and this, just doing that, taking back the Einstein condition, the Einstein AdS action is endowed with the correct counterterms, and there is no mismatch any longer, and it looks like a very fundamental way of repairing the previous problem. This is what I was mentioning. We are discussing with Nicolas Boulanger, who is an expert in conformal invariance in higher dimensions, trying to extend this result to higher dimensions as well. Also, in a different line of research, we have been very much interested in the consequences in higher codimension of the addition of topological terms and boundary terms in general in the computation of holographic entanglement entropy. Holographic entanglement entropy, you require that there is a conical singularity in the space-time, and automatically you induce something in codimension 2, in 2 dimensions lower. So for instance, if you start from Einstein-Hilbert action, what you will induce is area in codimension 2. But this entangling region that people consider touches the conformal boundary. And because it touches the conformal boundary, this area, the concept of area is divergent. And you need to renormalize the area as well. And what we realize, and we really like this concept, that if we start from a renormalized volume, we induce in codimension 2 a renormalized area. Because what we induce, if we add topological terms, we add topological terms in codimension 2, and we are removing all the divergent terms coming from the points where the entangling region touches the conformal boundary. So it's a nice concept. And this is also what we are dealing with, computation of holographic entanglement entropy, and seeing this contribution as conformal invariance also in dimension 2. Thank you.
Thank you very much, Rodrigo, for this very clear and it's inspiring talk. Are there questions for Rodrigo?
Please just open the microphone and ask.
Hi, Rodrigo. Thank you for the nice talk. I was wondering about what about the contribution of the term form to the boundary stress tensor, but in general, without asking any asymptotically locally AdS behavior, thinking of, for instance, other kind of asymptotics, namely Lifshitz with a fixed critical exponent or something like that. What about in that case? Is this procedure working on that direction as well?
Yeah, this is in principle problematic beyond what is this particular asymptotic behavior. The truth is that if you add the chain form, you cannot define such a thing as the canonical momentum associated to the Gauss connector. It's a very technical thing, but the point is that the point is that you cannot associate anything that looks like Brown-York stress tensor in terms of the full boundary metric. What you can do is working out the holographic picture. And if for a different asymptotics, I cannot tell you. I cannot guarantee that there is such a thing. In asymptotic Lifshitz, there is still a holographic interpretation, but of different type. It may be the case that we have evidence in previous papers at the level of solutions that topological terms can cure the divergences of also certain type of Lifshitz asymptotics. Not all. And if you ask me what else you have to add on top of this to render the action finite, I have no idea, because this looks very fundamental thing, and once again you cannot just patch up your model with the additional terms that you can work out. I mean, it had to be something more fundamental, I would say.
I see. Thank you. So when you say that there is no way to define a canonical momentum when you add the term form, do you mean that this is identically zero, or there is a pathological thing? Or
let me explain. This is exactly the same as the problem. I mean, Einstein-Hilbert action is a topological term in 2 dimensions. If you add the Gibbons-Hawking term, you define this canonical momentum for Einstein-Hilbert can be expressed as a totally antisymmetric Kronecker delta of 3 indices. If you are at the boundary, no, of 2 indices, I'm sorry. If you are at the boundary of 2 dimensions, this is identically 0. This is the other way of seeing this topological contribution. Whenever you are dealing with topological terms of the Lovelock type, I mean of the Euler type that gives rise to Lovelock terms in higher dimensions, you cannot do this construction. It's a technical thing. It's a technical issue. The canonical momentum is identically 0.
I see. Thank you, Rodrigo.
Okay, so I guess that okay, there is another question, but probably so maybe we can postpone it to the discussion session and have a short break.
Remy.
Yes, but I can really wait. So
it's up to you.
Yeah, let's wait because I have more technical. Like I want to discuss some expressions, so it's not
okay.
Right.
So thank you very much. Okay. Yeah.
So it can be postponed for the discussion session.
Yeah, we have 1 hour to discuss for all the questions that there are. So let's meet here in 4 or 5 minutes, and then we will have the second talk. Okay.